Hello everyone, I am G. Vaishali, bearing roll number 447. Today, I am going to present a seminar on the subject signals and systems. My topic is about the what is Fourier transform from Fourier series. Fourier transform from Fourier series and singularity function is my topic. Understanding the transition from discrete to continuous frequency analysis. This is the basic concept, the introduction. Fourier series to Fourier transform. The Fourier series and the Fourier transform are closely related. They both express functions in terms of sinusoids, sines, and cosines, or complex exponentials. The key difference lies in the domain of function. Fourier series applies to periodic function, and Fourier transform applied to non-periodic function. Here, periodic functions are which repeats itself. That means the signal repeats itself. It is continuous, and the Fourier transform is non-periodic, which is discontinued there, and it is up to some point which is non-periodic function. And Fourier series for periodic function. This is the basic definition formula. And a function f of t, it can be written as a sum of harmonics. F of t equals to sigma n equals to minus infinity to infinity Cn into e power I 2 pi mt by capital T, where Cn equals to 1 by t capital integral minus t by 2 to t by t f of t e power minus I 2 pi nt by capital T dt. Here Cn is the Fourier coefficient. It is very important when we are solving the problems. This formula C naught, Cn and Bn are important factors to solve the any problem in Fourier series and exponential transformation. Basic Fourier transform definition. For a function f of t, its Fourier transform f of omega is defined as f of omega equals to minus infinity to infinity f of t into e power minus j omega t dt. The the parameters f of omega is a frequency domain representation, complex function of frequency. F of t is the time domain signal, can be real or complex. Omega is the angular frequency in radians and seconds. J is the imaginary unit. J square equals to minus 1. We all know I square equals to minus 1. We can keep any one, J or I. Fourier transform inclusion. Frequency content of a general non-periodic signal. They are real discussing what is a non-periodic signal, which is uh, do not repeat itself. Time domain versus frequency domain. We see time domain versus frequency domain and time domain signal and its frequency domain spectrum. From Fourier series to Fourier transform, the conversion. Now imagine what happens when the period capital T tends to infinity, the time period. That is, the function becomes non-periodic. The frequency components become continuous, not discrete. The function transforms from periodic to non-periodic and discrete to continuous. As t tends to infinity, the Fourier series turns into Fourier transform. When the time period becomes infinity, the Fourier series turns into the Fourier transform. The formula is given by f of t equals to integral minus infinity to infinity f of omega into e power I omega t d omega, where f of omega equals to 1 by 2 pi integral minus infinity to infinity f of t into e power minus I omega t dt. This is the Fourier transform. It tells you how much of frequency omega is present in the signal f of t. The Fourier transform generally tells that how much of frequency, that is, it is represented by denoted by omega, is present in the signal f of t. In our class notes, we assume the f of t as x of t. We can say anything x of t or f of t. Example problem. We see example problem that convert the Fourier series of a rectangular pulse train to the Fourier transform of a singular rectangular pulse. We see step by step the procedure. Define the periodic signal first. Let's start with a periodic rectangular pulse spring xt of t equals to, it is a range 1 where mod t less than a by 2, 0 or otherwise, and this pulse repeats every capital T seconds, so it's periodic. We see now here the terms are repeating itself, then it is periodic. Step 2. Find the Fourier series coefficients. For periodic signals, the Fourier series is xt of t equals to sigma n equals to minus infinity to infinity cn into e power j n omega naught t, where omega naught equals to t 2 pi by t, where we always take the t value as time period t equals to 2 pi. Omega naught equals 2 pi by 2 pi equals to 1. The basic wide conditions we use omega naught as 1. To find the Cn coefficients, we see how to find Cn coefficients. Cn equals to 1 by t into 2 sine n omega naught a by 2 by n omega naught. This comes as a by t into sine c n omega naught a by 2 pi. This is the formula of Cn, the final formula. Step 3. Convert the Fourier transform as time period. T tends to infinity. When we convert the time period to infinity, it becomes periodic. As t tends to infinity, the signal becomes aperiodic. In NDL, it became periodic. Now, then t tends to infinity, it becomes aperiodic. A signal pulse, omega naught equals to 2 pi by t, we all know the LLC, the formula, tends to 0. Frequencies become continuous. When it becomes 0, the frequency becomes continuous. Replace the sum with integral. Here, the sum with integral. X of t equals to sigma cn into e power j n omega naught t times to x of t equals to integral minus infinity to infinity x of omega into e power j omega t d1. This formula converted as this one. Nothing, we just use an integral. Instead of summation, we converted into integral. We have this. Move to the next. Use correspondence n omega naught times to omega. Cn tends to 1 by 2 pi x of omega d omega. From earlier, Cn equals to a by t into sine c of n omega naught a by 2 pi. X of, let's take the omega equals to n omega naught. Listen to the pen. Omega equals to n omega naught. Cn equals to a by t into sine c of n omega naught a by 2 pi. X of omega equals to limit t tends to infinity. T into Cn equals to a into sine c omega a by 2 pi. N omega naught becomes omega. The final result is Fourier transform of a rectangular pulse. X of t equals to 1 if mod t less than a by 2 and 0 otherwise. X of omega equals to a into sine c omega a by 2 pi. This is the Fourier transform of a single rectangular pulse of width a. We saw the problem how to solve. This is an example problem. Let's move to the comparison table for Fourier series and Fourier transform. The comparison table and features Fourier series transform. If we see one by one, signal type. A Fourier series is a periodic and Fourier transform is a periodic. Frequency domain, discrete, continuous. Summation or integral. In Fourier series, we use summation for the formula. In Fourier transform, we use integral for the formula. Output coefficient Cn and spectrum for Fourier transform f of omega. This is the comparison table. We should remember this table. Another topic, singularity functions. The general singularity functions, also called discontinuity function or generalized function. These are the basic signals. Are special mathematical functions used in engineering and physics to represent sudden changes, discontinuous or localized effects in a compact way. The singularity function shows us how a signal suddenly changes or moves from one form to another form. These singularity functions are helpful to know. The main types of singularity functions. Unit step function, u of x minus a. The unit step function is, this is the unit step function. This is the graph. Unity is 1, no, that's 0 and 1. turns on at x equals to a, x minus a. It turns on when x equals to a. Definition: u of x minus a equals to 0 if x less than a, 1 if x greater than a. We can take this as a. Okay, example: a load applied suddenly at a point. Unit ramp function x minus a into u of x minus a. A line starting at x equals to a represents a gradually increasing effect starting at a point. If we see the graph is represented as the straight line from the origin. It is the unit ramp function is represented with r of t. The range is 0 for t less than 0 and 1 for t greater than or equals to 0. Line starting at t x equals to a. Here the x equals to a represents a gradually increasing effect starting at a point. Here the graph is started at gradually increasing from here to here. Unit impulse Dirac delta function. It is represented with del x of a. Unit ramp is r of t, and unit step is u of t. Unit impulse is del of t. Unit impulse Dirac delta function. Infinite at exactly x equals to 0. Elsewhere integrate to 1. Here integral minus infinity to infinity. Del of x minus a dx equals to 1. Models concentrated loads or instantaneous changes. This is the presentation on the signals and system on the topic Fourier series of transforms and singularity functions. This is the end. Thank you.